this next video, we want to continue our discussion of trying to understand limits of sequences. And we'll start by talking about some more complicated limits than we did in the previous video, limits that have fractions or square roots or other types of functions in them. And the main idea is that if we have a fraction, for example, we're going to factor out the highest power of n in the numerator and in the denominator. So we'll factor out these powers of n, and then the rest of the limit will be easier to understand. So this is the kind of thing that makes most sense if you give an example. So let's say that an is n to the fourth plus n cubed minus 2 over n squared minus 1. So what do I mean factor out the highest power of n in the numerator and denominator? The highest power of n that occurs in the numerator is this n to the fourth. And the highest power of n that occurs in the denominator is n squared. So we're going to write the numerator as n to the fourth times something, and the denominator as n squared times something. So for this to work, the numerator should be 1 plus 1 over n minus 2 over n to the fourth. And the denominator then should be 1 minus 1 over n squared. Why does this help? Well, now when we take the limit as n goes to infinity, n to the fourth over n squared, that's just n squared, times we have this 1 plus 1 over n minus 2 over n to the fourth over 1 minus 1 over n squared. Well, what's happening in the numerator as n goes to infinity? The first term is going to 1, the second term is going to 0, and the third term is going to 0. Because in each of the last two terms, the numerator is just some number, and the denominator goes to 0 as n goes to infinity. And in the denominator, 1 is just 1. But as n goes to infinity, minus 1 over n squared goes to 0. So as n goes to infinity, n squared goes to infinity. This is going to infinity. And the rest of the limit is going to something like 1 plus 0 minus 0 over 1 minus 0, which is just 1 over 1, which is 1. So this limit is something like something going to infinity times something going to 1. So this is infinite. So this sequence diverges. Let's do another example. Let's look at one with a square root. Let's say an equals square root of n squared plus n over n plus 2. So let's do the same idea. Let's factor out the highest power of n in the numerator and the denominator. First, let's write the numerator as square root of n squared. Well, OK, let me do this in more steps. We can write it as square root of n squared times 1 plus 1 over n. And the highest power of n in the denominator is n. So let's write the denominator as n times 1 plus 2 over n. And we can now factor this out. This is square root of n squared times square root of 1 plus 1 over n, divided by n times 1 plus 2 over n. But square root of n squared is just n. So we get n over n times square root of 1 plus 1 over n divided by 1 plus 2 over n. Now these n's cancel. We just get square root of 1 plus 1 over n divided by 1 plus 2 over n. So now, when we take the limit as n goes to infinity of an, that's the limit as n goes to infinity of square root of 1 plus 1 over n divided by 1 plus 2 over n. And as n goes to infinity, 1 plus 1 over n goes to 1 plus 0. We get something that's going to square root of 1, which is 1, divided by something that's going to 1 plus 2 over n goes to 0. So we get another 1 plus 0. We just get something that looks like square root of 1 plus 0 over 1 plus 0, which is just 1 over 1, which is 1. So this example converges to 1. So I'll pause and erase, and then I'll go over one other technique called rationalizing that helps quite a lot when you deal with an expression that has radicals. The last technique we'll discuss here is called rationalizing. If you have an expression that looks like square root of a minus b, the thing to do is to multiply by the conjugate form of this expression. We're going to multiply by square root of a plus b divided by square root of a plus b. The idea is that when we multiply a function by 1, we're not changing that function. But this is going to allow us to algebraically simplify things a little bit. This is easiest to see with an example. So let's let an be square root of n plus 3 minus square root of n. So here, I mean, this is of the form square root of a minus b, but b is square root of n. So what we're going to do is take this expression and multiply by the conjugate form, which is square root of n plus 3 plus square root of n over square root of n plus 3 plus square root of n. Now, what do we get in the numerator? Square root of n plus 3 times square root of n plus 3 is n plus 3. Square root of n plus 3 plus square root of n. OK, multiply those. We get square root of n plus 3 times square root of n. But then the next term we add is minus square root of n times square root of n plus 3. So these cancel out. And then we just have to add negative square root of n times positive square root of n. So we get minus n. The denominator just is the same as it was, square root of n plus 3 over square root of n. So what we get is 3 over square root of n plus 3 plus square root of n. And now we can see what happens when we take the limit. The limit as n goes to infinity of an is now the limit as n goes to infinity of 3 over square root of n plus 3 plus square root of n. As n goes to infinity, the numerator is always 3, and the denominator is going to infinity. So we're getting is 3 over something larger and larger and larger. This limit exists and is 0. So this sequence converges to 0. So these are a few techniques for understanding limits of sequences. In the next video, we'll focus on a really important one, which is how to apply L'Hopital's rule to understand limits of sequences.